Good morning, everyone. Hope you're all doing well. Ooh, it is cold outside. My husband is an architect and he works from home as well, and he gets the closer room to the internet because he has to use Revit and some really high capacity softwares. So I get banished to the back room and there's no insulation under the floor. So it is absolutely freezing. So you may see these last couple weeks me in just like full winter gear. So we're in a pretty good place for the semester. We are moving into the last chapter, if you can believe it. Oh my goodness. This is on acids and bases. A lot of it will be sort of crossover from the solutions chapter because acids and bases are usually introduced to reactions as solutions or dissolved in water. So yeah, let's see. Quick look at the syllabus here, just a reminder. So we're sitting here and we've already gotten through solutions, which is great. So what we can do is start acids and bases this week, finish acids and bases up next week. Your test won't be until next Sunday, not the end of this week, but the end of next week. But what that will do is give us a little bit more room right in here to review for the final exam. So always nice to have additional review. So before next week, before the final exam review, I'd recommend going through all the other chapters. And I'm not saying that you're going to do some like really intense studying, but at least look through the chapters and go, okay, yeah, chapter 2 measurements, I can do conversion factors in my sleep now, right? Oh, I don't remember nomenclature. Oh, I don't remember chemical bonding. Okay, so make just a couple notes on what you feel strong on and what you don't. And then when you come to review next week, when we're talking about reviewing stuff, you can have really poignant questions. Hey, can you please do Lewis dot structures? Can you please do nomenclature with polyatomic ions? So at least you will know what you don't know. The worst is to not know what you don't know. Okay, so at least if you go through it, you'll know what you don't know, and then hopefully you'll remedy that before the exam. All right, so chapter 14, last chapter, acids and bases. Acids have been used in spy movies and other thrillers to dissolve metal bars. Okay, so here he's got a little pen and it's got a secret compartment with acid in it and he's melting the bars. Is that possible? It is actually. You can dissolve water, or I mean, you can dissolve metal using an acid, but you would probably need more than what can be contained in that little pen. Sour Patch Kids and lemons. These are all examples of acids. Acidic things tend to have a nice sour taste to them. So citric acid and tartic acid are both things that we find in lots of sour candies. Why does it give it that kind of soury taste to it? Even just looking at that lemon, it makes my mouth kind of water. It's because the citric and tartic acids from the Sour Patch Kids will combine with the saliva that's in your mouth, and it forms these little H pluses. And you're going to want to get in the habit of seeing an H plus and thinking, that's an acid, all right? And those H plus ions will react with certain molecules on your tongue that can give it that sour taste. So the protein molecule that it specifically reacts with will send an electrical signal or a nerve impulse to your brain, and then you experience a sour taste. And you can actually sort of simulate or experience that even without the H+, because our bodies are very, very cool things. And just by actually looking at something sour, you can get that. Acids dissolve metals. This is true. So with enough acid, it would be possible to dissolve an iron bar, but that amount would not fit in a pen. And we'll look a little bit later about how this happens, this dissolution of metal with acid. So here are some of the properties of acids. Acids have a sour taste. Acids dissolve many metals, not all metals, but most metals. And then, this one, not super important, but acids turn blue litmus paper red. So there's a paper here. You may have used it before, and it's blue. And if you dip it in an acidic solution, it will shift to a red color. Here's an example of an acid. This is most common that you'll find in laboratory settings, also in your stomach, hydrochloric acid, HCl. So there is a hydrogen and there is a chlorine molecule, and these two are bonded to each other. When we stick this thing in water though, this chlorine and this hydrogen will break apart, and this hydrogen or H+, or sometimes we call it a proton, will float around in solution, and that is what gives it the acidic quality. We find this in industry to clean metals, prepare processed foods. Isn't that appetizing? Refined metal ore. And then again, it's the main component of stomach acid. So this acidic material helps to kill any harmful bacteria that may be entering your system through your food. So there is bacteria on all of the foods that you eat. You just don't get sick because you have this nice acidic stomach. Now, sometimes that bacteria can be so dramatic that it can overpower the killing capacity of the hydrochloric acid. If you've ever had indigestion or heartburn, the reason it has that sour taste or that sort of burning acidity, acid feeling is because it's literally hydrochloric acid coming up through your esophagus. Here are some other acids. So we have sulfuric acid on the left here and nitric acid on the right here. These guys are a little bit more complicated as far as the compounds are. I don't expect you to know the Lewis structure for these, but this, the formula for this, sulfuric acid. So this we call a diprotic acid. Diprotic in that you get di, or two hydrogens in every one molecule. So you get a little more bang for your buck there. There's the sulfate molecule. Here we've got nitric acid. This is a monoprotic acid, or there's just one hydrogen mixed with a polyatomic ion. So here's our polyatomic ion, and the hydrogen sort of got shoved onto one of the oxygens. Sulfuric acid is the most widely produced chemical in the United States. 36 million tons, it's probably more than that now. These are both used in laboratory settings. And then sulfuric acid and nitric acid are used to make fertilizers, right? Which we grow a lot of food here, so that is an important component. Also used for explosives. Anything that you can use to make, not anything, but a lot of things that you can use to make fertilizers are also very useful for making explosives. Those go kind of hand in hand. Dyes and glue. And then we find sulfuric acid in automobile batteries. So if you've ever changed your battery, things like that, battery acid, sulfuric acid. Here we've got acetic acid. Acetic acid is found in a lot of wines. The word vinegar originates from the French word vinaigre, which means sour wine, so acidic quality. And then acetic acid, this thing here is an example of what's known as a carboxylic acid. And so carboxylic acid is it's an organic functional group, and we haven't gone into organics, and we won't go into organics a whole lot, but really at all. But if it has this thing right here, we call it the COOH, C-O-O-H, or it's a carbon that's double bonded to an oxygen, single bonded to another oxygen that's bonded to a hydrogen. This formation here is known as a carboxylic acid group. So looking at this molecule here, we can see in the acetic acid, the COOH group is happening right here. So it's a COOH group that is pretty much attached to what we would call a methyl group. If you're like, what is that? Don't stress too much about it, okay? I'm not gonna test you on the organic stuff. We've got citric acid over here. See, they start to get pretty complicated and clunky. We've got malic acid. These are both carboxylic acids. We find these a lot in living organisms. If we've got an acid, we've got something to counteract that, which is known as a base. Here are some of the properties of bases. Bases tend to have a bitter taste to us, to humans. Bases have a slippery feel, and bases will turn red litmus paper blue. So there is if you use some sort of indicator paper, it will change color consistently if it's a base. So bases feel slippery. So all these cleaning products over here contain bases. Bases tend to feel slippery because they'll react with oil on your skin and they form sort of this soap-like substance. Soap in general is basic, and that's what gives it that quality. So whereas acidic stuff, there's sort of an appetizing feel to it. Like, ooh, I want like, a butter lemon pasta sauce, right? That sounds kind of yummy, or Sour Patch Kids. Our bodies are good with digesting more acidic stuff. More basic things have this kind of bitter taste to it. We do eat basic things, but in general, basic stuff tends to be a little bit more, we have a more adverse taste reference to it because it is poisonous a lot of times. So bases are less common in foods because of their bitter taste. And we have specifically an aversion to these things called alkaloids, which are organic bases that are found in plants. And a lot of times these alkaloids tend to be poisonous. So we don't want to eat them. So they taste icky. There are some things that contain bases. Coffee is actually acidic overall. So if you have like an upset stomach, you usually don't want to drink coffee because the acidic component of it will make it make your stomach worse, right? It'll give you worse indigestion. But the reason that coffee kind of tastes bitter is because caffeine itself is a base. So here's a caffeine molecule over here. It itself is basic, but it's kind of drowned in an acidic solution. The overall coffee is acidic. I love coffee. I learn everything I can about coffee. So some of the bases that you may be comfortable with right now: sodium hydroxide, potassium hydroxide, and sodium bicarbonate. These are all very common in lab settings. Also in manufacturing, we see them a lot in manufacturing, and then they're all over cleaning supplies. So if you go and were to look at some of the ingredients in your cleaning supplies, you would see all these things. Another interesting place that we see bases in everyday is an antacid. So if you do have indigestion, you can take antacid, which is sodium bicarbonate, and that helps to neutralize stomach acid so that you have a more neutral pH in your stomach. It's not so acidic. I have my cousin, one of my favorite cousins, whenever he eats like really crappy food, he has to take antacids. I mean, he eats them like candies. I also ate antacid like candies when I was pregnant, but I sent him a group text with all my cousins and asked everybody how many we thought he ate for Thanksgiving. And I put in 5, and I guess I think the right answer was 8. He ate 8 on Thanksgiving Day. So stomach was a little upset. So how we classify an acid, we have a couple different definitions of acids and bases. This first one, the Arrhenius definition of an acid. This is the simplest definition of an acid, and it doesn't encompass all acids. All right, so we will have a little bit broader definition, but for this one, it gets you, 90% of the way there, at least for acids. So an acid will be anything that when you stick it in water, it's going to produce an H+ molecule. So that hydrochloric acid that's over there, that's aqueous in water, or it will create an aqueous solution, so it'll dissolve in water. These H's and the Cl's will break apart, and they specifically break apart into their ions, okay? So they'll have this charge to them. So we've created sort of an electrolyte solution. So we ionize the H plus and the Cl minus. So there we've got our HCl and it breaks apart. Note that this H plus ion is super reactive. So sometimes this H plus will bond with a surrounding water molecule because if it's in an aqueous solution, there are a plethora of water molecules. And what we'll get is this H plus will combine with a water molecule. See, here's our O, here's our H's, and then there's two lone pairs. This will just sort of stick to one of these ends and you'll get this thing here, which is called H3O plus. This is the hydronium ion, okay, not hydroxide ion. Hydroxide is OH. That's more to do with base. Hydronium is an acidic thing. So in water, we're always going to have H plus ions and H2O molecules associating with each other. So because of that, chemists will often use this H plus or this H3O plus. So either of these things can be used interchangeably. So you might see things written with an H plus, or you might see them written with an H3O plus. They're talking about the same thing. They're talking about the quantity of acid. Sometimes you may even see this written as a proton, because what is an H plus? Well, an H plus is a hydrogen with its electron ripped off. Hydrogen has one proton, it has no neutrons, and one electron. If you rip its electron off, all you're left with is a proton. So when looking at a formula, I would not expect you to know how to do it off of a structure, but off of a formula, the ionizable hydrogen, or the hydrogen that will pop off into solution and form an H plus, is always written first. Okay, so when looking at this formula here for formic acid, the hydrogen sitting out in front is going to be ionizable. The hydrogen that's nestled into the rest of the formula, that's the non-ionizable hydrogen. That thing isn't going to come off. We can see it in this structure here. The H that is bonded to this exterior oxygen is really easy for that thing to pop off. This H that's nestled in with the carbon, that is not as easy to remove, right? You have to do something much more than just drop it in water. Again, I wouldn't expect you to look at this structure and say, oh, it's this hydrogen, not this hydrogen, but I would expect you to look at this and I could say, hey, how many ionizable hydrogens are there? And the answer would be 1, because this guy is non-ionizable. Under the Arrhenius definition of a base would just be anything that produces OH ions in solution. So NaOH is an Arrhenius base because it produces OH in solution. So there's our sodium hydroxide, and then bam, we put it in water and there are our OH. NaOH is an ionic compound, so it's a little different than the HCl, which is not ionic. This breaks apart into ions, and it will completely dissociate into its ions. It's important to note that if we look at something like a molecular compound like what would be methanol, CH3OH, again, this is more in the organic realm, so I wouldn't expect you to know how to name this and stuff, but looking at this, this is not ionic, right? This is a non-metal, 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 non-metal. This is a molecular compound. That OH will not fall off, okay? It has to be a metal combined with the OH. So this would not dissociate as a base. This definition of Arrhenius definition, or this definition of an Arrhenius base is limited, okay? So it doesn't explain a lot of bases out there. So if we stick with just this simplified definition of an Arrhenius definition, and it doesn't really matter what acid and what base it is, like it could be hydrochloric acid, it could be hydrofluoric acid, it could be sodium hydroxide, it could be calcium hydroxide, whatever it happens to be, the overall net ionic equation will always be this. We have an acidic thing, so we have an H plus, doesn't matter what delivers the H plus. We have a basic thing, an OH minus, again, doesn't matter what delivers that. Those two things will come together and neutralize to form water. So acid plus a base gives us neutral pH. Think of an acidic, really, really acidic stomach. You add an antacid and you get a pH that's a little bit more neutralized. So the Arrhenius definitions of acids and bases cannot explain why some substances will act as a base, even if they don't have OH in them. So one example of this is NH3. I'm gonna have trouble with my trackpad. So NH3 or ammonia. This is a base, but looking at it, you can't tell that it's a base off of the Arrhenius definition because there's no OH in place. So the Arrhenius definition just doesn't do a really good job of explaining these bases. So we have to expand our understanding into what's known as the Bronsted-Lowry definition of acids and bases. And how the Bronsted-Lowry definition differs is that instead of thinking of an acid is something that produces H plus and a base is something that produces OH minus, we think about the transfer of the H plus. And the H plus again is considered a proton. So in this definition, we think of one as being the proton donor and one as being the proton acceptor. Specifically, the acid is a proton donor. So the acid will donate, it donates an H plus. A base will accept an H plus. So there's no OH in this definition here with bases. We just are talking about what's happening with the H plus. Is it giving it or is it taking it, accepting it? In 1923, Johannes Bronsted was working in Denmark and Thomas Lowry was working in England, and they developed this concept of transferring the proton independently but simultaneously. That's why it's called the Bronsted-Lowry. That happens actually quite often in science where you get a situation where there's been a lot of research done in an area and then two people that are not working together, they don't know anything about each other, will come up with the same concept like within a week of each other. It's pretty interesting to see that happen. So let's look at something that we know to be an acid, okay? HCl, hydrochloric acid. But if we look at the Bronsted-Lowry definition, if I take hydrochloric acid and I put it in water, what will happen is that this H will pop off and it will stick to the water molecule and I get the H3O plus, and remember that's the hydronium ion, that's an acidic thing, plus the Cl minus. This definition more clearly accounts for what actually happens to the H plus. So this is acting as an acid. Why? Because it is donating an H plus. And so then you may be thinking, well, isn't the water accepting the H plus? Yeah, the water is actually accepting the H plus. So that makes water a base in this equation here. Water is, and we'll talk about it a little bit later, but water is amphoteric, which means it can act as an acid or a base, depending on the situation. Let's look at this one here. So NH3, I told you all that this was a base, but you can't really see it from just looking at the formula. So if we put it into an equation where we drop it into water, what happens here? We've got NH3 with water, and this will pretty much steal a hydrogen from the water. So it becomes NH4 plus, right? It's added a hydrogen, and the water is now down a hydrogen. So the water has donated and the NH3 has accepted. That under the Bronsted-Lowry would make this an acid and it would make this a base. So the water is acting as an acid. Well, if this NH3 if it has the ability to steal a hydrogen from water, what is left over? Your OH minus. So you've indirectly been able to produce OH. Instead of dissociating to produce the OH, you've stolen from the water and made the water OH. So when looking at your Bronsted-Lowry definition, you have to be able to determine what's the acid, what's the base, and then you also need to classify what's known as a conjugate acid and a conjugate base. And the way that I figure this out is I find the two things on each side that sort of look like each other. So this thing and this thing look like each other. They're just separated by a hydrogen, right? This has one more hydrogen, this has one less hydrogen. And then this thing looks like this thing, and it's just separated by, again, a hydrogen. So this has one more hydrogen, this has one less hydrogen. And then you have to ask yourself, well, what is happening to get from the left side to the right side? For this to become this, it has to accept, right? Accept. If you're accepting an H plus, that makes you a base. Here, this thing is donating. So this is going to donate an H plus. If you donate an H plus, that makes you an acid. Now, every base will be paired up with what's known as a conjugate acid. Because if I was to flip this equation, we've got arrows going in both directions. If I was to flip this, I could go in the reverse direction. And what happens? Well, this is an acid and it donates to become the conjugate base. So the acid and the base are always on the left side. The conjugate acid and the conjugate base will always be on the right. Once you've figured out one of these four components, it's real easy to fill the other ones in, because you're never going to have an acid and an acid on the same side. You'll always have a base and an acid. And you're never going to have an acid combined with a conjugate acid. It'll always be combined with its conjugate base. So if you know that this is a base, then right there you can determine this is an acid. If this is a base, its buddy over here has to be the acid. If this is the acid, its buddy has to be the base. They all sort of fall into place once you've gotten one of them. So some substances, and it's not just water, but water is a very common one, can be either an acid or a base, meaning they can either accept or donate a proton. So in this instance, the water is accepting, so it's acting as an acid. In that previous one with the hydrochloric acid, the water is, here it's donating, here it's accepting, so it's acting as a base. So amphoteric just being either acidic or basic. So in that one equation we had looked at, there was the NH3, which was the base, and then the conjugate acid here, which would be ammonium, which would be NH4 plus. How do these differ from each other? Well, if it's a base becoming its conjugate acid, you add H plus. Remember, that has a charge to it. So not only do you increase the hydrogens, you increase its charge by 1. Okay. The opposite is true if you have an acid and you're trying to figure out what its conjugate base is. You have to remove an H plus. So you have to take a hydrogen and you have to drop the charge by 1. Here it had a neutral charge. Here it's got a negative charge. So here's another acid-base situation. This is sulfuric acid. This is a diprotic acid. Now, do know if you have a diprotic or a triprotic acid, these are acids with more than one hydrogen that can ionize. You ionize them individually. So you don't ionize both hydrogens at the same time. You would ionize the first hydrogen and then the second one. So pairing these off, this guy is buddied with this guy. All right. This guy is buddied with this guy because they look like each other. What happens to get from here to here? I have to donate a hydrogen. Whenever I donate, that's an acid. This guy has to accept a hydrogen, so he becomes the base, and then you fill in your conjugate acid base. Let's do a couple Bronsted-Lowry examples outside of this. I'll give you two. I'll give you the first one. And no. What am I doing? Okay, so I want you to tell me what is acting as the acid, what is acting as the base, and then what's the conjugate acid in the base. But then I'll give you one more. Okay, so I'll give you another 2 minutes or so to work through both of those. Okay, so in both of these, let's see, we've got the way that I go about it is I pair them off. So this guy looks a lot like this guy. And then this guy looks like this guy. So how do I get from here to here? I have to donate an H plus. So if I'm donating, that means that this is an acid. This is an acid. This has to be its conjugate base. And then I don't even really need to ask what's happening here, because if this is an acid, this has to be a base, but let's ask anyway. What is happening here? This is accepting H plus. So this makes it, a base. And this is its conjugate acid. This one down here, this guy looks like this guy. And this guy looks like this guy. How do I get from here to here? I have to accept an H plus. That makes this a base. If this is a base, this has to be an acid. If this is a base, this has to be its conjugate acid. If this is the acid, this has to be the conjugate base. Okay. So here, water is acting as a base. Here, water is acting as an acid. Any questions on that? No. So neutralization reactions, this isn't really anything new. We kind of went over this already with in our reactions chapter, but when an acid and a base are mixed, the H plus from the acid and the OH from the base will combine to produce H2O and usually some sort of salt. So here's our acid, here's our base, our products will be water and a salt. The salt contains the cation from the base and the anion from the acid. And then the net ionic equation, which we can see here is, because again, if we were to stretch this out and just look at what the important thing is, the Cl is just a delivery system for the H. The K is just a delivery system for the OH. So the net ionic equation would be H plus that OH minus to give us liquid water. So another neutralization reaction, specifically of carbonates or bicarbonates. So those are things that contain CO3 or 2 minus or HCO3 minus. They will produce water, salt, and then also carbon dioxide gas. And this is a gas evolution reaction. So here I've got hydrochloric acid, and it's combining with sodium bicarbonate. And we get our water, there's our salt. The added thing in there is CO2, which we didn't have before, coming from the carbonate. Acids will react with metals in a way that causes the metal to dissolve. And when I say dissolve, it means that it goes into solution. So if we look at this equation down here, I've got hydrochloric acid, and it combines with magnesium. And notice what the phase is on the magnesium here. Here, the magnesium is a solid. Okay, so it's a rigid, solid thing that we can see. When I combine it with the hydrochloric acid, the magnesium will go through a single displacement reaction where it combines with the chlorine and it becomes an ionic compound or a metal ion. So here I've got magnesium chloride. It swaps places with the hydrogen. In the process of doing this, it becomes an aqueous solution. So now when it has combined with the chlorine, it's actually able to dissolve in your water solution. And then there's also the hydrogen gas that's being given off. That's why it fizzes or bubbles. We can see this happening with all different sorts of metals. So here with magnesium, there it is, it becomes an aqueous salt. Zinc also becomes an aqueous salt. Iron will also do this. There are some metals out there that don't react with acids. If the bars were made out of gold, a pen with hydrochloric acid would not dissolve those. If we happen to be taking, acid and we're combining it not just with metal, but with a metal oxide, in this case, we produce water and a salt. I don't test you really on this here. We are not going to get into the neutralization reaction of alum. This is something that you explore in 151 though. Okay, so a titration. So we've already talked about solution stoichiometry, and you've already, you've already done your calculations for solution stoichiometry, so this shouldn't feel too foreign, but we're going to apply it to titration. So in a titration, we have a known concentration of one of our reactants and an unknown concentration of the other thing. So let's say in here, I know the concentration of hydrochloric acid. I don't happen to know the concentration of the NaOH. Well, what I can do is take the concentration of my hydrochloric acid and my volume, and then if I know the volume of how much NaOH it required to neutralize, I can work backwards to figure out the concentration of the NaOH. So how that works is, let's say I have my HCl, there's these H pluses in solution, right? If I start to drop OHs in, from like a basic solution. Those OHs are going to combine with the H plus to form little water molecules. At some point, you will pour enough of this base into your acid where every single H plus is combined with an equal amount of OH. So you get to a neutral pH, or you reach what's known as your equivalence point, where there isn't more acid or more base. They are equal to each other. Now, how do you know you've reached your equivalence point, right? Because you can't see it with the naked eye. You have to add what's known as an indicator. And this is a dye whose color will depend on the acidity of the solution. So its color will change depending on how acidic it is. And it will actually turn, a lot of times we use phenolphthalein. Sorry, I don't know, I keep yawning this morning. We'll use phenolphthalein, and what that does is it will turn this sort of light pinkish color when you've hit your equivalence point. So here's before titration. This is during titration. So what happens is you drop some of the base in and you'll get this like very like faint hint of pink, and then the pink will disappear. Because what will happen is you're reaching your equivalence point in a very small portion, right where it got dropped, and then it's diluting back out with the rest of the acid and you lose the pink. At some point though, the entire solution reaches equivalence and it's all mixed and even, and you get this pretty pink color, and that's when you know you've reached your equivalence point. And in this column here, you've got volumetric measurements on it, so you can determine how much of the, let's say, the base you used to titrate a certain volume of the acid. So here is a titration problem. It says 10 milliliters of an HCl solution of unknown concentration requires 12.54 milliliters of a 0.100 molar NaOH solution to reach your equivalence point. What is the concentration of the hydrochloric acid? So this is just solution stoichiometry. So we're going to figure out what compound A is and what compound B is. So compound A in this situation is what we have more information on. It's the NaOH. So let's put NaOH. And what do I know about it? Well, I know its concentration. So its concentration is 0.100 big M NaOH. Again, when we're doing solution stoichiometry, just get out of the big M and convert it into moles per liter. So 0.100 moles of NaOH in every 1 liter of the NaOH solution. I also know the volume, right? 12.54 milliliters. And I've told you guys with solution stoichiometry as well, just get out of milliliters and get it right into liters. So 0.01254 liters of the solution of the NaOH. Okay, compound B is going to be the HCl. What do we know about that? We know its volume. Its volume is 10 milliliters. Let's just get that into liters right away, 0.010 liters. And then we want to figure out its concentration. So we want to figure out its molarity. What is its molarity? And remember, molarity equals moles over liter. Well, here's my liter value right there. So I just need moles of HCl. Right? Well, if I know this information, if I know the volume, I can use the molarity to get into moles of NaOH, and then a balanced equation will get me into HCl. They don't give us a balanced equation here, but HCl plus NaOH, remember, an acid and a base will produce water, H2O, and a salt. The Na is going to combine with the Cl, NaCl, and it's balanced. So this is a 1-to-1 coefficient ratio. So back from our flow chart for solution stoichiometry, in this case, we're going to go volume A into moles of A, into moles of B, into, in this case, we want to figure out the molarity of B, big M. So start with our volume A. We've got 0.01254 liters of NaOH. I'm going to multiply that by my molarity, and I'm going to keep it in this direction because if I leave the moles on top, that means I convert into moles of NaOH, right? And then from here, we've got 1 liter of the NaOH solution. So I'm just using this value right here. The liters cancel. Now I want to go, so that got me from here to here. Now I want to go from moles of A into moles of B. How do we do that? Well, we use the coefficients, and fortunately, this is a 1-to-1. So for every 1 mole of NaOH off of my equation, I get 1 mole of HCl. 1 mole of HCl. Cancels right there. You could stop here because you have your moles of hydrochloric acid, right? So solve for this and then plug it right into the equation. I'm going to just actually chain this volume in here and just say, hey, 1 and then 0.010 liters. So I'm just going to take my mole value and divide it by the liter value. It's the same thing as plugging into the equation. Why do I put the 1 over? Just to fill in the space. Does the liter cancel with the mole? No, it doesn't. And so my unit at the end of this dimensional analysis would be mole per liter. If you don't like doing that, just stop here and then plug it into the equation. So running that through our calculator, 0.01254 times 0.100 divided by 0.01 gives us a volume, or rather a molarity of 0.125 moles per liter, or I can say it is 0.125 liters of your HCl. Any questions on that? I mean, it's just more solution stoichiometry. So they did the same thing. They converted here milliliters into liters, and then liters into moles, and then moles into moles, and then they plugged it into their equation. Ended up with the same answer. So I'm going to give you guys a titration problem to do on your own, and then we'll go over it. Let's type it up. Give me just a second. Don't write this down yet. I have to think of how I want to word this. I'm going to change this up. What comes in. I'm going to say 55 milliliters of HCl is neutralized by 25 milliliters of 0.25 NaOH solution. What is the HCl concentration? Okie dokie. So 55 milliliters of HCl is neutralized by 25 milliliters of a 0.25 molar NaOH solution. What is the HCl concentration? I'm gonna have you work on this on your own. It's very similar to the last one we did. figure out, I'd write a balanced equation. It's the same balanced equation. Figure out compound A, compound B, what path you want to take, what your knowns are, go from there. So I'll give you 7 minutes for this one. Just another 30 seconds or so, and then I will, I'll go over this one with y'all. Okay, so compound A, what we have more information on is our NaOH. So I'm going to put the NaOH here and put the HCl over here as our compound B, or where we're headed towards. What do I know about compound A? I know its volume, which is 25 milliliters. I'm just going to right off the bat convert that to 0.025 liters. Move the decimal over 1, 2, 3. So 0.025 liters of the NaOH. Our concentration is 0.25 big M. And again, I'm going to convert that into moles per liter because it's more useful in dimensional analysis. So 0.25 moles of NaOH given in every 1 liter of the solution. Compound B, I know my volume. Volume is 55 milliliters. So again, I'm going to just convert that to 0.055 liters of the HCl. We want to figure out concentration. So concentration is molarity, and molarity equals moles per liter. I know liter. It's down there, so I really just need to get moles of HCl. So let's get started. We start volume A to moles of A to moles of B into, in this case, we're going to molarity of B. Start with our volume A, 0.025 liters of NaOH, and we're going to multiply it by its concentration, 0.25 moles NaOH in every 1 liter of the NaOH solution. That cancels. Then we need to use our equation, HCl plus NaOH produces H2O plus NaCl, and it's balanced, so it's 1:1. Don't always assume it's 1:1, but in this case it is 1:1. So 1 mole of NaOH for 1 mole of HCl. We can stop there and then plug it into our equation. So let's do that. We'll stop there. We get 0.025 times the 0.25. And I get a small value, but we're dealing with really small volumes, so that's all right. 0.00625 moles of HCl. I'm going to keep all those numbers. I'll round it to 2 on the next step. So in order to get molarity, right, molarity equals moles over liter. Well, here's my moles. So 0.00625 moles. And we know the liters because that was given to us, 0.055 liters. Right, it was 55 liters, milliliters, right? Yeah, okay. And this thing equals 0.1, well, it's 113, so we'll just go with 11 moles per liter, or that's the same thing as saying 0.11 big M, specifically of HCl. So there's our concentration. Does anyone have any questions on that, on solution stoichiometry? Radio silence out there. Okay. Hopefully that means that we've gone over it enough times that you feel relatively comfortable with solution stoichiometry. Hopefully. So when talking about acids and bases, we can narrow it down into what we would call strong acid, strong and weak acids and bases. So HCl is an example of a strong acid. HF is an example of a weak acid. Strong acids mean that they completely dissociate or completely ionize in solution. So every hydrogen and every chlorine is going to break apart. A weak acid like hydrofluoric acid, some of it will ionize, but some of it will recombine and stay as the molecule HF. So what we can see is here we've taken hydrochloric acid and we've dropped it in water. There's a single arrow, and the single arrow denotes that it's complete ionization. So every H and every Cl break up and we get these hydronium ions and then the chlorines. So lots of H3O pluses happening in solution. As far as how this relates to conducting electricity, okay, pure water is not a good conductor of electricity because there aren't a lot of charged particles. If we have something with charged particles, like for instance, dissociated acid or ionized acid, the more of these charged particles you have in solution, the stronger its capacity to conduct electricity because the electrical current can pass through these charged particles. So if something is a strong acid, it's got a lot of these, we're going to expect it to have a very good conductivity. So here over on the left, we have pure water. We've got a light bulb, it's attached to a battery, and they're running the current through pure water. And the electrical current can't make the jump from one to the other to light the light bulb and complete the circuit. But if we're dealing with hydrochloric acid in solution, the electrical current can run through, it can hop over this bridge and make its way to the light bulb to complete the current. So we would have a nice bright light bulb. Here are the strong acids that we have. There are 6 strong acids. 5 of them are monoprotic, so hydrochloric, hydrobromic, hydroiodic, nitric, and perchloric. They all contain 1 hydrogen. Sulfuric acid, which is also a strong acid, is a diprotic acid. Remember, diprotics, you remove 1 acid or 1 H at a time. Anything that isn't one of these 6 would be a weak acid. That's how you know weak acids. It's just not one of these. Hydrofluoric acid is not on this list. So what happens in hydrofluoric acid is some of the HF is being ionized by the H2O, and we're getting this H3O plus, but there's a double arrow, meaning that some of it is actually going back to its molecular form. So what we'll find is that we have some H3O pluses and F minuses. We've got the ionization happening, but then we just have some of the molecule, the hunky acid molecule. And actually we have quite a bit more of the HF than we do the ionized H3O pluses. So we're dissociating and then we're recombining. In this case, we've got our pure water, no conduction of electricity. If we have a weak acid, our light bulb will shine, but it's not very bright because the electrical current can make the jump because there are some charged particles, but it's kind of dulled. So we get a weaker light. There are many weak acids. Some of them are organic and some are inorganic. Most carboxylic acids are weak acids. Again, that's getting a little bit into the organic realm. But in general, if you have a strong acid and you dissociate it, you can always assume that whatever the concentration of the molecular acid is what the concentration of the H plus or the H3O plus is. So if I've got this here, HCl, this is a strong acid. So if this has a concentration of 1.5 molar, my concentration of my H plus should also be 1.5 because every H and every Cl are breaking apart, so equal concentrations. Now this over here, this is a weak acid. So the overall concentration of my molecular acid is 3 molar. How much H am I getting? It's something less than 3. All right, it's the H3O plus is just going to be less than the 3 because every H and every C2H3O2 are not breaking apart. Some of them are staying combined. So just know with a strong acid, it's an equal concentration. To a weak acid, it is just something less. This over here, if I have a 2.5 molar HNO3 solution, I know that this is a strong acid. So my H3O plus concentration should also be 2.5. Determine the H3O plus concentration on all these guys. All right, this is a weak acid. This is a strong acid. This is a weak acid. So these will be less and this will be equal. As far as strong bases are concerned, a strong base is one that completely dissociates in solution. So strong bases, the metals from the first and the second column, in those first three rows, combined with OH, those are all strong acids. Oops, sorry. Where are we? There we are. Do note though that unlike diprotic acids, which ionize in 2 steps, bases, if they have 2 OHs, they dissociate in 1 step. So if you had like calcium hydroxide, you wouldn't rip off 1 OH and then have to rip the second one off. They would all come off together. So here's our NaOH, and it breaks apart. If every Na and every OH break apart from each other, then we have a strong base. A weak base is similar, analogous to a weak acid. Unlike strong bases, the OH and will dissociate, but it will also recombine. So here we've got our base, it's combining with water. The base steals one of these H's to make the water the OH minus, but this will recombine. In this equation, the B is acting as just some sort of generic weak base. NH3 is an example of a weak base. It partially ionizes. So some of the NH3s will steal from the water, some of them will give the H back. There are a lot of weak acids, organic amines, for your information, are weak acids. Here's ammonia. How can we tell that these are weak acids? Well, for the sake of this class, because it's sort of simplified, that double arrow is a really good indicator. The double arrow lets you know that you're dealing with a weak acid. Anything that isn't, where were they? These guys are going to be, or I'm sorry, weak bases. We're talking about bases. Anything that isn't these will be weak bases. So the double arrow will indicate a weak base, and it will also indicate a weak acid. So this says determine the OH concentration for each of the following solutions. So again, you just want to determine if it's weak or strong. If it's strong, like this one is strong, we can assume the concentration of OH is equal to the total concentration. So equal. This is weak because it's not one of those strong bases. So it's going to be something less than the 0.35. And then this one is strong. So we can say that it's not only is it equal for this one, but it's equal and it's double because you get 2 OHs. So we would take our concentration, 0.025, and we'd multiply it by 2. Okay, so we're gonna stop off there. We've got, the last section is, has to do with calculations. So I don't wanna get started into KW and all that just yet. So we'll finish that up on Monday. We may even have some time on Monday to start our final review. So this weekend, if you can please take a peek at your overall syllabus and just look at the chapters so that you have an idea of what you want to ask. Otherwise, have a really good weekend. Just homework lab stuff due, but exam will be next Sunday. So I will see you all on Monday. If you got a question, hang out. Otherwise, enjoy your weekend.